We were solving the partial differential equation boundary value problem, the Laplace equation in particular, as exemplified, or a way to physically interpret it anyway. One physical interpretation is the heated plate, where the function u is the steady state temperature along the plate. So it's not a function of time, it's a function of location on the plate. Here is the partial differential equation itself, where x has a finite extent and y has a finite extent. We already solved it for these boundary conditions. Now let's solve it for different boundary conditions. In fact, we'll solve it for the temperature is going to be 0 along the bottom and 0 along the top. It's going to have specified temperatures as a function of y along the sides. Let's get to that problem. So same partial differential equation. Here it says where y equals 0 and y equals 1. So the y dimension is 1 unit. But those temperatures are 0, the bottom and top. That's what these two conditions say. At the other sides, where x equals 0 and x equals 1, so x is also 0 to 1, so this is a square plate of unit length. It's some function of y on each side. On one side, it's just a constant, and on the other side, it's just this linear. So we not only need to separate the variables of the equation, which we already did, we need to separate variables from the boundary condition. So when y equals 0, the whole thing equals 0. That means y at little y equals 0 is 0, and the other one says y at little y equals 1 is 0. So let's look at, we separated them, right? Here's how they separate. I guess I could put the negative sign on either side, but I'll put it with the y side. But that leads me, if I set it to plus lambda, if I set my separating constant to plus lambda, I get this equation in y, and I have complete boundary conditions, so I can do the eigenvalue problem on y in this case. That's why I used a plus lambda as a separating constant when I put the negative sign with the y's. So now let's go through the y example. So here's the y equation, ordinary differential equation with its boundary conditions. Here I go through the entire eigenvalue problem, but it is just case A that we've already solved, I think, at least twice already. And when you do that, you get these eigenvalues. Oops, you get these eigenvalues and these eigenfunctions for the y equation. Then we have to use the same eigenvalues for the x equation. Here was the x equation with a negative sign. So it has positive lambda. So the x solution is this mix of Cauchy Singe. So I have these solutions for y, these for x. I multiply them together and add them up for all n's. Here is my general solution. It satisfies the equation itself and these two boundary conditions. I still have these boundary conditions left to satisfy. So let's go through that. One boundary condition said when x equals 0, the temperature is 10y, some given function of y. If x equals 0, what happens? Singe is 0 and Cauchy is 1, so it's just base of n sine of n pi y. So that's my general solution when x equals 0, and that has to equal 10y. Well, I have to expand 10y in a sine series. You need the table of the sine series of the Fourier series to do this. The way we did it, what we called P to match this, it equals 1. P equals 1. I think it's big L, or whatever. It's in the Fourier series table, set P equal 1 to match this. And then we have, by matching coefficients, that means this big A sub n is the little a sub n's in the sine series. You look it up in the table, this the integral you'd have to evaluate. It's kind of a painful integral. I use the table. Sine, you get this evaluated between these limits. Let's see. Sine of either 0 or n pi is going to be 0. Bottom limit y is 0. So you're only left with n pi 1 cosine of n pi, and cosine of n pi is minus 1 to the n. Anyway, all this mess, the big A sub n's reduced to that. That's only one boundary condition, one more boundary condition. We still got the last boundary condition. So we have what the A sub n's are. Here's our general solution, but now we know what the big A sub n's are. Other condition was on, let's see, where was it? Here it was, it's on the derivative of u with respect to x. We need to take that derivative. This, go back to the general solution and take its derivative, you can do this. Remember, the derivative of a cosh is sinh, and the derivative of a sinh is cosh. We have this, and when x equals 1, here's what you have in the solution, and the boundary condition says that's got to be minus 1. So we need to expand minus 1 sine series. So this whole mess here, by matching coefficients, all this stuff up here, this in parentheses, has to equal the coefficients of the sine series, which if you look up in the sine Fourier sine table, it's an integral. When you evaluate that integral, you get this. So we get this mess equals that. Yeah, we're dividing by n pi, and there was already an n pi squared. And we already knew what the A sub n's are. They're these things. Anyway, when you put it all together, you get a fairly big mess. And I'm not going to go through that simplification. Here's what the B's are, and here's what the A's are. We now have the complete solution. A complete solution. Here's the solution. The big A sub n's are these, big B sub n's. This, since you have cosh in the denominator, we could call it the hyperbolic. That was kind of tedious, a little bit messy, but we went through a whole problem once again.